Can you hear me now better? Okay, thank you very much. So this is a kind of topic that we have studied for quite a long time, and in a very classical material, which is barium titanate ceramics. But this time I will show you that even very classical and old topic can bring some new questions, maybe more than answers. This is mainly the subject of a PhD thesis of our student Vlad Alexandru Lukac that was ended with the collaborations from the group members and with the collaboration from Jacob Jones, Andrea Bencian and Marco De Luca. When speaking about scaling phenomena in ferroelectrics, everybody, if you know that we refer to the changes, the modifications of properties induced by the reduction of the size of the entity. It can be particle diameter in powders or grain size in ceramics or thickness in films. As intrinsic effect, these phenomena are expected because ferroelectricity is a long-range order phenomena that is become unstable when you reduce the physical size of the system. Apart the intrinsic effects, there are extrinsic effects related to the boundaries. The three types of systems that I have mentioned, powders, films, or ceramics, are subjected to very different electrical and mechanical boundary conditions, and therefore their influence on the functional properties and on the structural stability can be very different. I know this is a community that works mainly in films, but unfortunately we are working only in ceramics, and the results that I will present apply also in thick films only, apart the ceramics. Okay, this is the outlook of my talk. I'm going to directly into the introductory part, the motivation of our study. Barium titanate, such an old material, ferroelectric material that have been discovered about 70 years ago, present a few structural polymorphs in different ranges of temperature. Assigned to these polymorphs, we have a polarization that changed the direction in rhomboidal, orthorhombic, tetragonal states below the Curie temperature, and polarization disappears completely in the ferroparaphase transition when the system turns into a nonpolar cubic state. All these transitions, structural transitions, are first order, and the properties, the physical properties, like in many cases, the phase transition, they are subjected to some anomalies, to peaks, to maxima. Like, for example, the permittivity that has this kind of jumps. This is a crystal A-axis permittivity, because the C-axis, the polar axis, the permittivity measured on along the polar axis is very low. Practically in ceramics, we have an average due to the random orientation of grains. Well, this transition temperature have been discovered by multiple experimental data, including quite recent ones, that change, they shift with reducing grain size. The rhomboidal orthorhombic and orthorhombic tetragonal transition move towards higher temperature when we reduce the grain size, while the cubic to tetragonal transformation move towards lower values, when we reduce the grain size. Practically the range, the extension of tetragonal state tend to reduce strongly when we decrease the grain size. This effect is predicted also by Landau theory, and as I said before, it was confirmed by many data, including the recent ones that have been included in the group of Penn State by these stars, which correspond to the very new ceramics prepared by the new method of low temperature sintering. A very interesting observation of this diagram is related to the fact that practically fine grain size are described by so-called pseudocubic phases, because the distortion in all the phases, rhomboidal, orthorhombic or tetragonal, are quite low, and practically the system is almost cubic. And another observation is related to the temperature, to the so-called room temperature, which is a very bad defined practically temperature, because what does it mean, room temperature, when here, as you can see, we are close to the orthorhombic to tetragonal transition from grain size, for grain sizes above 100 nanometers, while in this range, we are practically close to all the transformation transitions. Practically here they merge in the same point. So when one reports the properties at room temperature should be aware that it might be here or close to this range, and practically the system is close. Even our barium titanate that everybody believes that is tetragonal practically is close to a range of phase instability. There are some simplified Landau calculations, and Leontin Pădurară, our colleagues, performed calculations, Landau-based calculations for ceramic materials, for ceramic barium titanate, in which he looked not only to the stable minimum, to the absolute minimum of the free energy, but also to the metastable state, to the other minima. And practically, he found many ranges of phase coexistence, which were not reported before. But here, before of that, I wanted to show that for the same temperature, a coarse ceramic can be orthorhombic, and a fine one can be rhombohedral, or to 13, for example, degree C, coarse one can be tetragonal and fine one can be orthorhombic, or above 100 degrees C can be both tetragonal, and in the ferroelectric case they can be cubic, of course. I was speaking about if looking to the metastable free energies instead only to the absolute minima of the free energy, you find quite large ranges of phase coexistence, which are represented here by this mixed color. For example, this color corresponds to 50% rhombohedral and orthorhombic phase in this range that accompany the main transition, that this would be the transition corresponding to the minimum of the free energy only. Well, we have therefore large temperature ranges for phase coexistence, and as experimental data also have shown, the room temperature sits practically in such a range of polymorph coexistence in barium titanate ceramic at any grain size. Well, typically when you reduce the size of the system, irrespective if it is a film thickness or grain size or particle size, almost all the properties scale, they decay when they show a decay, like this one. Here it is the spontaneous polarization has a decay, tetragonality, or other parameters, with the exception of dielectric constant. Dielectric constant in barium titanate has, according to a collection of data, dated to a few years ago, that I collected for this chapter, and according to many other reviews that are published, show a maximum around 1 micrometer. They show a decay only below this size, but they show also a decay in the for large grain sizes. These data show a very clear trend, irrespective of source of powders, method of preparation, stoichiometry, stress density, or defects. And for a given grain size, there is a variability up to about 1,000, 2,000 maybe difference between permittivities, which was explained at that time, let's say at the level of maybe 10 years ago, like coming from the purity of grain boundaries. If the grain boundaries are clean and free of defects, people consider that they will obtain higher permittivity. If there are plenty of defects, the permittivity would be low. Well, some recent data, this diagram has been updated at the level of last year. And in addition, as I forgot to say, not only permittivity, but also piezoelectric coefficients show a peak around 1 micrometer, but more recent data and more good collection of data that has been done by the group of Vincenzo Buscaglia. According to them, that I discussed before, there is a second maximum here. I would say that is a very spread data collection in this range, but anyway, there is a clear maximum around 1 micrometer. Traditionally, the mechanism for this maximum was considered similar both for permittivity and for D33, but it's a discussion about this. Maybe I'll have time to say. So if up to 7 years ago, the big interest was focused on this range because it was related to the interest about how to preserve a high permittivity level above 1000 when you reduce the physical size of the particles of the grains below 100 nanometers. In the last 5 years, maybe, appeared some studies that, again, focus on this range of the permittivity maximum. And also, for solid solution, people search if there is a similar maximum, if titanium or barium are substituted to some levels. Why is interest on this maximum? Because it enhanced permittivity. So if you have a relaxor state in solid solution that gives you 10,000 or 20,000 permittivity, if you can still increase with 50%, this would be great. Anyway, as interpretation for these contributions to this maximum, there are some quite old and some that were recently accepted to be the final one, the definitive one, explanation for this behavior. First of all, the intrinsic contribution, it is considered to be grain size independent. So no reasons to have a maximum according to the lattice were found in by many experiments. Then it was the interpretation of Alt and Hennings in the 80s. Mostly Alt performed some studies. According to him, the fundamental role in this maximum is given by the residual stress contributions that somehow are maximized around this grain size due to the fact that at this level of grain size in barium titanate ceramics, the arrangement of 90-degree domain walls is favorable due to the dependence of domain wall length on the grain size that was confirmed by this law. Like 5 years ago, 6 years ago, these two studies decided, concluded that, like for example, this study from the group of Jacob Jones, that domain wall displacement is the origin of superior permittivity and piezoelectricity. So no other effects, but the role of domain walls. And this somehow was confirmed also by this last paper in the topic of TAN. I would stress on the paper of the group of Jones, because they have shown that in a range of grain sizes that they have chosen around the critical size of 1 micrometer, they found that internal stress as determined by diffraction analysis is grain size independent or is the same, while by analyzing the interplay between the peaks 02 to 00 under the application of hysteresis loop cycle, the fields, by applying in situ this field and analyzing the structure under high energy source, they concluded, as I said before, that domain walls are the origin of this maximum. Okay, so this is the interpretation, the accepted interpretation concerning this maximum. Why here is a maximum of both domain wall mobility that was really probed by the group from North Carolina State University, but also it is claimed the maximum of domain walls. Practically, there are some nanoscale studies showing that here the number of domain walls is increased, but there is not a study along all this range of sizes. Well, we wanted to study if the phase coexistence has some role or it is modifying the grain size effects that were quite well known in typical tetragonal barium titanate, and to see if this interpretation related to domain walls is valid, or is observed also in this case. We preferred, with respect to other studies, we prefer to keep the same type of powder and to obtain a range intermediate range of grain sizes by using a two-step sintering method. One, it is a field and pressure assisted by spark plasma sintering, in which we prefer to use the same parameters for all the samples, because spark plasma sintering is a highly non-equilibrium process, and we wanted to not change really these parameters, to start at least with the same level of densified ceramics for the second step, which is a grain growth pressureless sintering step, allowing us to obtain the desired range of grain sizes. According to the first step, we just consolidated the powders, because the level of grain sizes that we have obtained is about the same. 70-80 nanometers is the same like in the starting powders that we have used, and densities around 90. The maximum was 93. While after the second steps, we could obtain densities in the range of 90 to 98, almost full densification, but I will report only exclusively the data with the high density, because I do not want to include the discussion about porosity. I will show you that we have effects of porosity as well. And all of them have been post-sintered to reoxidize them, because the SPS is a strongly reducing process. These are the selected microstructures with quite homogeneous grain size in this range and with high densities. Including in the range of the critical one, we have a few sizes. And again, here are only the dense ones that I would like to report. So the structural study with state-of-the-art XRD shows that for high grain sizes, we have a tendency towards orthorhombic state, while for small one, we have a Bichur multiphase here. And for the small ones, for the fine ones, we have a tendency, this peak is higher, is not pure tetragonal, because the ratio of this peak should be half, but here we have a tendency towards tetragonal, and we started from pseudo-cubic powder. The Rietveld analysis indicated that we have a phase superposition of mainly orthorhombic and tetragonal phases, half, let's say, in this range, and then with a tendency, as I said, to orthorhombic state for high grain size and tetragonal for small grain sizes. At that moment, when we saw that our samples were orthorhombic, we prepared many groups of set of samples by using similar or modified parameters, because we wanted to obtain tetragonal barium titanate, as everybody reports. However, after we found that most of them are orthorhombic, we looked better to the literature, and we found that in the last 10 years, there are some groups that reported lower symmetry phases in the tetragonal-based state of barium titanate, either induced by some actions like field or by stresses, or present in some specific conditions as metastable state, monoclinic or orthorhombic or other states. Of course, the room temperature property should be affected by this phase superposition. And there is a paper like 10 years ago in which they used similar sintering parameters like us, and indeed also they obtained a tendency from tetragonal, that is state, that is found for small fine grain sizes and porous, because here there are two parameters, porosity and grain size, by the method that they use to sinter the samples. and the tendency towards orthorhombic state for dense and high grain sized materials. And another very nice study that is 3 years ago of the group of WADA, in which not only the fact that by increasing temperature you can induce orthorhombic state or multi-phases, but they observed that some states, some symmetries can be induced by even by cutting or polishing the ceramic, and this can be removed after annealing. Here there are a few samples just polished or after annealing, 1 hour, 4 hours, and many hours and so on, or sintered by different procedures. And this have been observed also, okay, we are not chemists, but we started 10 years ago to prepare samples. We have doubts about the purity, about the method, about the stoichiometry and so on. But in the same time, in the group of Vincenzo Buscaglia, they were preparing barium titanate and everything was orthorhombic. And then they realized that they just were changing the cutting machine for the ceramic. So it was due to a specific cutting machine that was different than the previous one. So no tetragonal barium titanate was obtained at that time. Then okay, here are many samples. We checked the reproducibility of the method, and we wanted to see if this orthorhombic state is still present or stable if you repeat or if you prepare different samples. As a tendency, we found that high porosity favored the tetragonal state instead of orthorhombic one, and this gave us an idea that stresses can be the origin. And here I can show you just that similar by different set of samples that we have prepared, but always by the same powder. The similar density, relative density, shows orthorhombic state like this one. While, for example, here, the 450 nanometers, if it is high porosity, is quite tetragonal, and if it is dense, it tends to become more orthorhombic because peaks are inverted between the red graphs here. What it was nice to see is that we get just the same grain sizes by the method, so we validated the reproducibility of grain sizes, but from one sample to another one we had a variability of porosity, and that's why I decided to report only the dense one. Our results are showing a volume effect because we didn't use any cutting machine. These are just prepared samples. They have a multi-peak behavior at room temperature. And because we wanted also to rule out the role of porosity, we prepared samples having the same grain size, but different porosity levels by using polymer sacrificial templates. We have a level of porosity from 4% to 26% here, showing clearly the inverted peaks, which are nevertheless multi-phase and with the tendency to be orthorhombic when they are dense and more tetragonal when they are porous. So the classical idea that barium titanate is tetragonal maybe should be, well, when we look to the literature, we discovered that many papers that report tetragonal phase have inverted peaks, like here, and not as should be for tetragonal ones. And also, even ourselves in a paper studying grain size effects, we found again inverted peaks, but we didn't even look because it was splitting. We said that it's tetragonal and that's on. So this is, that conclusion is that always one should check these effects. So my colleague Cristina Ciomaga studied a bit the role of polling in changing this phase superposition at a qualitative level without calculations. I will explain why. Okay, because we observed in the tunability data, I give here some specific grain sizes, that there is a change in slope to a field of about, here is a DC field, about 10 kilovolts per centimeter. So she have polled these samples with the same field level at room temperature, and as you can see, after refreshment, polling, or as prepared sample, they look different. So we can change, if we have a range of phase instability, by applying a field, or like other people did, by polishing, they could change the phase. We investigated better this system before, and we have already published this in a material that we knew that should be orthorhombic at room temperature, in a solid solution of barium titanate that was recognized by everybody to be orthorhombic at room temperature. But for barium titanate, we still had these doubts, and therefore we decided to perform. We had a plan after discussions with Jacob Jones to resolve the structure, to see the stress level, because we suspected that they have an important role, and to perform in situ both temperature and field dependence, as they did in their former study. Well, we sent the samples, then the pandemic arrived, and we could obtain, after these 2 years, only the temperature-dependent structural analysis, which nevertheless shows very interesting things. The multi-peak behavior was confirmed. We have, these are the peaks around 45 degrees, where it is this splitting. The presence of multi-phase here is confirmed by in different range of temperatures. And okay, by fits, we could find for a few selected grain sizes. We could observe the phases that are known of barium titanate. For this one that is very fine, we find pseudo-cubic state, or maybe orthorhombic, but anyway, peaks could not be deconvoluted. Here, we find orthorhombic in all the other ceramics below 10 degrees C. We found cubic states above 120. Here again, we couldn't see any phase transition, but nevertheless, we detected it. Tetragonally in the middle, a large range of phase superposition around the temperature, which, if you look better, they tend to become larger. Okay, here is large, but here is a big mess. And become thinner, this temperature range, when you increase the grain size. So we have a multi-peak behavior for all the samples. Is not only specific to small grain size, like they were reported and like they were calculated by Landau models, but they are present for everything. Here we also could detect at the end of story the presence of Curie temperature around 120 degrees for the finest ceramics, by looking the evolution of O2 profiles with respect to 111 that is not subjected to splitting in barium titanate around the Curie temperature. Anyway, but the structure was not resolved because we couldn't have good data for Rietveld resulted from the high energy analysis. So we know that is a multi-peak, that many phases are there, and they are changing with temperature, but we don't know exactly the amount of each phase that is there. So the low field dielectric properties confirm this maximum, and with respect to other publications, we are in the high range of permittivities in these samples. And also we could reproduce this kind of temperature versus grain size phase diagram, which was completed with calorimetry and Raman data from Marco De Luca. Typically, the low field dielectric properties can be also analyzed by relay analysis, which is quite rich in some information because it can separate the field-independent permittivity that is due to the lattice or intrinsic contribution, and reversible domain wall vibrations. The reversible domain wall vibrations are related to the oscillations of domain walls along local minima. Of course, we are in relay analysis is performed under sub-switching fields who are 20 times smaller than the coercive field, and we could separate this contribution with a very clear maximum of the field-independent permittivity and with no critical behavior of the nonlinear parameter. So the component that is given by the intrinsic and reversible domain walls shows this maximum, but the others not. Okay, this is a ferroelectricity decay that is known by many systems, and also our ceramics look the same trend. What it is was strange for us at the moment of investigation was that while before even dense ceramics obtained by spark plasma sintering didn't show any hysteresis loop, these ones that have a multi-phase show a loop even at 75 nanometer grain size. And this was the same for other samples that we have prepared in this set, which show us the fact that these are somehow different, and most probably the origin is the existence of orthorhombic state that is giving us 12 positions for the polarization reversal. And tunability show us something very nice. The fact that even at high field, this maximum is preserved, which put questions about the role of domain walls, because what kind of domain walls one can have close to the saturation. If you look, this pink curve is always up, even to very high fields. And okay, the interpretation related to the role of domain walls maybe should be questioned again. Moreover, we found the existence of a peak even at high temperatures when the system should be cubic, so when we should not have domain walls. Maybe there are some reasons for this behavior that should be further checked, and maybe the intrinsic component is grain size dependent, or some defects. So as there are some publications that show that at high temperatures in the cubic phase there are still some nanopolar nanoclusters that are static in origin, and they may contribute in some way to this maximum, or even the theory of fault should be reconsidered. So when we try to look to the origin of polymer superposition, why we have a polymer stabilization with respect to other samples that we have investigated by a high-resolution TM study of Andrea Bencian, it was demonstrated that we have no impurities, no boundary effects, no segregations. For example, the spectral analysis inside or at the border of grains show just the same composition, and the presence of titanium only. Usually, hydrothermal synthesized powders may present some internal nanoporosity, which was not found here. But instead, what is very interesting and not reported yet, I don't know if you can see very well, there are regions with crystallographic defects, which are extended defects along 100 planes in 100 and 110 zone axis, which by low angle angular dark field mode, okay, here maybe you can see better, they demonstrated to be strained. So we have here strained internal strains in the starting powder. Again, no impurities around this one. The composition is just the same around this defect and out when we have no defect. They are about 2.5 nanometers long, and they form loops. They are closed loops. And again, the presence of titanium 4+ only. Further, with these powders, we have the ceramics. The sinter ceramic show internal defects mostly inside the grain, inner part of the grains, which are like dislocations. They look like dislocations. They are irregular in size or distribution. Somehow at the boundaries it was not found any of this defect. It means they are in a way released or compensated, and the grain boundaries are very clean and separate regions of single crystalline character. So at the end, maybe by looking to some data in literature, dislocations are the origin of phase superposition. Somehow, by creating this internal stress, they stabilize the multiphase, or they stabilize the orthorhombic state in dense materials. They can be to some extent released when the material is porous, and they may be responsible with some enhanced properties, and if one understands how to control or to promote them, maybe they will obtain, like we found here by chance, I would say, higher permittivity, higher polarization than in the classical tetragonal barium titanate ceramics. It is, okay, in a very recent paper, nice paper from the group of Darmstadt, that low constraint fields and elastic distortions around them, around these locations, present a multi-scale interaction with polarization and strength, and they may influence dramatically the properties. So I have more questions than conclusions, and I will end this presentation like this. With thank you very much for your presentation, for your invitation, and for the audience.
Thank you for your presentation. Okay, so we have time for one or two short questions.
You've shown the dielectric constant as a function of temperature, and it seemed to me like the peak between the orthorhombic and the tetragonal phase was reasonably sharp compared to the wide range of coexistence. So do you have any explanation for this apparent discrepancy?
No, okay. It is a discrepancy indeed, because, okay, maybe one expected to have this extended phase superposition only at very small grain sizes, but maybe there are all of these dislocations that are all over the range of grain sizes maintain this even when the grain size is higher. I don't know if you exactly means this.
My question is for any given grain size.
Yes.
The dielectric constant as a function of temperature.
Yes.
Shows a relatively sharp.
Yes, it is sharp.
The X-rays as a function of temperature show a wide range
Yes.
of coexistence.
Yes.
So, but for the same grain size.
Yes. Yes, this was strange also for us, because previously grain sizes in the same range, below 100 nanometers, they look very flat. So we wondered why still it is so sharp, the dielectric constant. Maybe the dislocation is the answer. I have no answer, really. Yes.
Just a short question, sir. You said that by cutting.
Yes.
By only cutting your sample, you shift from tetragonal
No,
to...
not us, no.
No,
this was observed by two groups.
Yeah. So the question is, if you know the size at which this appears, it's a millimeter, okay. It's half a millimeter, then I don't know.
Well, they performed in this paper that I have shown in the group of WADA, both state-of-the-art XRD experiments and the synchrotron radiation XRD, and they saw indeed that there is only a surface effect of, I don't know the size exactly, the penetration depth of the radiation in the two cases should be, yeah, yes, exactly.
Okay, thanks a lot for your presentation. I was asked to go to the stage to present the speakers for the online followers. So the next speaker is from Zeiss. It's a sponsor of this conference, already traditional sponsor, and the talk is about multimodal correlative microscopy. The presentation will be online, and the technical team will present it also for us here. Thank you.
On screen. Hello. Can you hear me?
Yes.
Okay.
Yes, we can hear you. Yes.
Perfect. And can you also see my screen as well, right? Okay. First of all, thank you very much for the opportunity to present our solution here in this workshop. This presentation is about multimodal correlative microscopy. Multimodal correlative microscopy is not really nothing new. It's also very well known as CLEM. for correlative light and electron microscopy. And the basic idea is to combine different modalities in join in one and the same sample. For instance, high resolution electron microscopy combined with fluorescence microscopy in one pictures, and thus you can see where, for instance, the fluorescence come from, or just add different kind of analytical modalities, which is more or less a standard like EDS. And recently, you can also correlate high resolution images from an ferroelectric electron microscope with mass spectrometry analysis. Means you are able really to see not only very low masses like boron and lithium and nitrogens, but also those isotopes. And another novel application is the combination of we say large field of view of electron microscopy images combined with IFM in one in the same images. But this is only one part of the story. Just get the maximum information out of your samples by combining different modalities. The second part of the story is just have those information in a huge context. Means you are like to pre-select the regions of interest of your experiment, of your samples in advance. For instance, with different techniques, there could be X-ray tomography, or there could be also X-ray tomography given by an synchrotron facility, and just give you the chance to analyze the huge vacuum sample, and even hidden sample, just means below the surface, and just select those regions of interest. And I think this is the most important part, because in the classical way, the CLEM or the correlative microscopy was traditional, made only in 2 dimensions, and now using this kind of 3D techniques like synchrotrons imaging capability, or in situ in lab X-ray microscope, you are able to even correlate 3D images. And that's where we are now. The microscopy become really in new dimensions, not only from 2 and 3D, but also in the dimension that you're able to just to combine different modalities in one image, to bridge different scales up to 6 orders of magnitudes from millimeter, even centimeter samples, showing details in nanometer resolution. This is the multidimensional, multi-instrumental, because all the correlation is not necessary to be performed in the one and single instrument. Means you need a kind of workflows that allow you to correlate coordinates in 2D and 3D between different modalities. Even those instruments not necessarily need to be in the same place. And of course, this is a multi-user, because you need here different expertises to produce this kind of information. And on the end, you will end with a huge amount of data that you need to analyze. Means on the end, you can imagine if you have a sample of cubic millimeter, that I will show you in this presentation, in the second part of the presentation, and that you are looking for details in the nanometer range in the whole sample, you will conclude with a enormous data amount of data. And this is the multimodal, dimensional microscopy that we are talking about, that I would like to present in this talk. For this, you need, of course, to do, you can imagine if you are talking about here about cubic millimeter or even cubic centimeter samples, you need to have a kind of workflows, how to combine this. We have, I will present 2 different types of modalities. The one is called shuttle and fines, which is, I will say, the most classical type of correlation microscopy for 2Ds, where more or less you have a common sample holder and you just move the sample holder through the different instrument and just by correlation mechanisms given by the kind of samples, you are able to correlate. The other dimension is to correlate images and modalities in 3D. Means you can start it with a kind of a synchrotron type of tomograph, or even in a lab Franken X-ray tomograph, and just combine with different 2D modalities. And we have here, you see here in these images, a couple of light microscopes and different types, but also electron microscope, or the so-called FIP, or the dual sand microscope. And in particular, if we want to have, for instance, for one cubic millimeter sample, the full resolution over the full cubic millimeter sample in nanopixel, you will need a special instrument. And this is something that we like to show you. What you see here, this is just, I would say, more or less the state-of-the-art microscope that you can find on the market today, from standard stereo microscope, over X-ray microscope, confocal microscope. And on the other end, you see here a single beam electron microscope in different modalities, field emission, conventional ECM. And in particular, I would like to emphasize the role of this kind of new instrument, because as I mentioned before, we are not only correlating 2D and 3D images, but you want, on the end, we want to, if we target, for instance, a huge sample, like a cubic millimeter sample, you want to see every single part of this volumina in a high resolution. And you can very easy imagine that if you want to image a cubic millimeter sample, just I had to stop this one here. If you want to image this cubic millimeter sample with a single beam at let's say couple of nanometers, 2 or 3 or 4 nanopixel, the scanning of those samples at this resolution, they will take years. The only way to bridge this the time in an, I would say, reasonable time of scanning time, is to use a so-called multi-SEM. Multi-SEM is a field emission electron microscope, as you know very well, but instead that they use a single beam, they use a bunch of up to 100 beams in parallel. And then you can just reduce the scanning time up to 2 orders of magnitude compared to a single beam SEM. And this is a key instrument for the multi-scale high-resolution correlative microscopy. Just in order that you have an idea how the system works, I would like to show you this movie. And we have here a field emission source that convert a single beam in multiple beams. This is here on the top, the samples. We scan the samples simultaneously with all the beams and create for every single beams secondary electrons, as is shown here, the green part, and collect all the secondary electrons via in-lens detector into the detector arrays. Means we have, in case, up to 91 single beams and 91 single in-lens detector collecting all the sample, all the signal simultaneously. And this is the only way to speed the process in order to create a very large image in 2D. Very large means really couple of square centimeters with a resolution of nanopixel, or even create a 3D images just by slice the samples, collect the 2Ds, and after this just doing a reconstruction. And the reason because I show in this instrument is because this is a key instrument for the multidimensional 2D and 3D high resolution microscopy. Okay, now I would like just to show you some examples of 2D and 3D high resolution correlated microscopy for very big samples. In this case, we have kind of a mega trends in science, which is the environmental health, showing here nanoplastic and microplastic in the environment. And what we see here on the middle, that is the samples. On the right, you see here, we are talking about here square millimeters of samples. We see here in a square millimeter scanning images with a resolution of with nanopixels, and you can see here an enlargement of those these images. And we are doing here, we identified very small particles in the range of couple of nanometers up to 20 nanometers, and then performs Raman spectroscopy. And why we do need both? Because in the Raman spectroscopy, you are not able to resolve the small particles because this model is based in a light microscope, and then only with the correlation you can really dedicated hit the single samples and performs the analysis to the Raman to characterize the different nanoplastic and nanoparticles, and only by correlation you can give you can see in a map distribution of different type of nanoplastic in your samples. And of course you can start to do a statistic to classify the particles by size, by the difference, and by the different type of polymers. In the second example, which is also a mega trend inside, is the investigation in lithium-ion batteries. And this is a classical multidimensional, multimodal approach, because we have a battery, which is a microscopic dimension, couple of cubic centimeters. And first of all, you take in a three-dimensional images with an X-ray microscope or with a synchrotron. You pre-select sorry, the area of interest, and thus make, for instance, a transversal cut. Observe the layer distribution with the light microscope. Everything here in the centimeter range. Now you have started to go down in resolution, also in size, and increase the resolution, and investigate single particle distribution up to nanometer dimension with the electron microscope. And then on the end, if you are pre-selecting any type of particles, you can really resolve it very well with the electron microscope. But what is wrong in this approach? Also, nothing is wrong. What is missing in this approach? That we have details, for instance, here in this, like this particle, but we are missing the context, because we identify a particle, but we don't have no idea how look like the neighbor particles at 100, 200, or the 1 millimeter distance. Why is so important? Because we need to analyze all those particles in a huge context to classify the distribution, the shape, the change of the chemical composition by cycling of the batteries. And therefore, we will need, in this case, an image of a huge area. You see here the scale bar. I hope you can see it. They are 0.2 millimeters, means we have here more or less in square millimeter sample scanning from the battery. We can also increase it up to square centimeters with a resolution of nanopixel, and then we can start to navigate and to classify the particles, to cluster the particles. Even here, we will need a special type of software to identify automatically different type of shape and particles. And on the end, you can even perform, I'm sorry, it was too fast. Sorry. On the end, you can even perform analytic composition. In this case, we are correlating mass spectrometry analysis here on the colorated image, showing distribution of lithium isotopes, different type of isotopes. In this case, isotope 6 and isotope 7, which play an important role by the development of lithium batteries, and put in the full context of the battery in a full context means in a context, in this case in 2 dimensions, of several square millimeter up to a square centimeter. And why it's so important to have this kind of instrument? Just to give an example or an estimation, if you try to do a scanning of a square centimeter of sample with nanopixel resolution, they will take weeks, only beam time scanning. But using this kind of multi-beam approach, field emission ECM, you can reduce the scanning time by 2 orders of magnitude. Means you will conclude in a couple of hours of scanning time and instead of weeks, right? This is just to give you the instrument needed in order to perform this huge context in images. And another example here, and it's what we see here. This is a correlation example using X-ray modality or synchrotron, if you want, modality, just to identify in a huge sample. In this case, this is a full microchips to identify the area of interest, the ROI that you want to finally analyze in higher resolution. And once you identify with this XRM the regions of interest, then you move to the next modality, which is in this case is the cross beam, or also the same technology, very well known as dual beam technology. And then you need to just to cut. You can imagine a microchip. This is in a very relatively big sample of at least 6 by 6 millimeter in size, and a thickness of a few millimeters, and you want to go really very deep inside. And if you try to do that with a dual beam or a FIP system, there's more or less impossible, because you will need also days just to reach the area of interest. And in this case, we use a correlated tool, which included a laser, a femto laser, just to cut very deep into the samples at the regions of interest. And the most important part here is that the coordinate system in 3D from the laser are correlated with the coordinate system from the synchrotron images, or in this case from the X-ray microscope. And once you really make a deep cut, you can see here the scale bars in millimeter range, then you move to the next modality, which is the cross beam using the gallium FIP or the FIP, just to polish the area of interest, and then finally to perform the images that you are aiming to analyze with nanopixel resolution. And this is a nice example, sorry, to show here how the 3D correlated microscopy work using different modalities. And another mega trend is the neuroscience. Of course, this is not the main topic here in the material conference, but this is, I would say, this is really the mega trends, because demonstrate where are the limits today for this kind of 3D correlated microscopy. And in this case, we are analyzing a piece of brain and try to see how the neurons are interconnected in this brain. And in this case, just to give you an impression, we take in a piece of brain. They are embedded in polymers. They are very fixed and ready to analyze with the electron microscope. And of course, it has a special treatment, which is very well known as osmium protocol, which allow you just to see with high contrast all the different area of interest. And just to give you an idea of what this means, and this is really a very recently publication, which was performed also in an correlative workflows using XRM, also X-ray tomography by synchrotrons or by in situ lab system, like in this case, using correlation with light microscopy, and finally using the multi-beam ECM just to take from these very huge samples this nanopixel resolution for the full cube, not only for a dedicated area of interest, but the full cube. It has performed with a resolution of nanopixel. You can see here the range of different neurons. And here, if you see here, the small square, it is here magnified on the corner. And you can see the interconnection between neurons in this huge volumina. And on the end, you get a graphic, which is just a few kilobyte big, and showing the interconnection. Just by the way, this cubic millimeter sample has a data volumina from few petabytes, and this is the next problem. And if you started just to roll up your experiment, and in the same time to reduce the resolution, the pixel resolution, you will conclude with a huge amount of data. And just you see here in this graph, the evolution on the last years, in the last decade, right, in the last 10 years, how the data volumina increase that you generated over the years. Just for a few years, for five years, we are typically ending with experiments in the range of gigabytes gigabyte images. But today, in this case of the brain experiment that I showed in the image before, we have scanned over 2,000 terabytes of data, and this has been scanned for 1.5 years ago. And the reason that as the publication is just happens a few months ago is because the scanning time of the few cubic millimeter they took with the multi-SEM more or less 6 months, but the segmentation of this cubic millimeter at nanometer resolution, they took more than 1 year using Google as partner computer center here for this investigation. And that's give you a dimension where we are now, if we are talking about correlation of very large area, or in the extreme case of 3D cubes of matter in nanometer pixel resolution. Now, in the second part, there was an introduction about, I would say, modalities, data management of 2D and 3D correlation microscopy. In the second part of my presentation, I would like to present you a workflow along in study case from a customer that we performed last year here in Oberkochen in Germany by a battery, very similar to the example that I provided you before, but in this case we are not talking about here about betabyte of images, but only just of terabyte. The most important point here is the correlation and the large size of the samples. The study was the target of the study was just to investigate in a huge context the particle change given by the cycle of our batteries just to see what is happening inside the battery after many cycles of charge and discharging. And what we did is here very similar as this example shown before. We took the big sample with the X-ray tomography just to select the area of interest, then move to the FIB system with a laser correlated cut system, and then move it again in the same tool to finally make the final polishment with the gallium FIB and correlate this lateral high resolution lateral image with an mass spectrometry analysis. And this is what is this study case about. Just here, just to remember how the workflow look like. We have here an area of interest identified by the X-ray tomogram just inside the samples, in the middle of the samples. We read out this 3D information from the aeroid with the laser inside the FIB here, and then started to cut everything around the area of interest just to analyze the surface. And finally, we image the surface and analyze the surface with the crossbeam. And on the end of the experiment, we performed from this given surface a mass spectrometry analysis and correlate these results with the high resolution images. And this is the case that I would like to show you. First of all, allow me just to this movie just to show you what is about a crossbeam laser FIB. What you see here is just a standard modeless state-of-the-art dual beam or crossbeam system equipped with an FL emission image part for electrons. We have a gallium FIB. Behind the gallium FIB is a mass spectrometer and a TOF SIMS. And on the right side, you see here a laser system. The most important part, the laser system are decoupled from the chamber of the microscope. They have an own vacuum chamber interconnected via an airlock, and you can shuttle the samples between both camera because both camera have the same coordinate system, and you can move the samples back and forth between laser and FIB or laser and electron microscope, mass spectrometer, without losing your coordinates. The second most important part is you can imagine if you are just cutting few cubic millimeter of samples, you produce a lot of stars of materials which will produce a lot of contamination into the microscope. And that is the reason because we here use a separated vacuum chamber and interconnected both chamber from the microscope and from the laser via an airlock in the microscope. This is a system which is recently launched last year, in August last year at the M1M in the US. And this is a size patented solution. And this is unique in this case that both chambers are fully separated and their coordinate system are correlated. And this is shown in this movie. You see how this works very easily here. You see here from the left, coming from the vacuum airlock, coming the sample you introduce to the electron microscope. This is the sample that you aim to analyze. Previously, you performed an X-ray tomogram just to identify the regions of interest shown here in this movie, and the regions of interest is somewhere inside the sample, just labeled here with a red dot. Then you make an image from the surface of with the electron microscope, and then fix the coordinate. Means you interpolate the area of interest to these 4 points. Then move it back to the laser system, and the laser system do the same. They will scan the sample, and then they will also correlate the coordinates from the electron microscope to the laser. They will read out the coordinates and then started to to take out all the materials that is not relevant for the investigation, just moving to the surface the area of interest. Moving back to the dual beam system, you see here the size, millimeter, thickness. We are performing now the final polishment with the gallium FIB, and finally we have our area of interest where we perform our high-end resolution images, and then you get very quickly this final results. And this is a nice example how a 3D correlation works. The point is, in this case study, we use these techniques. In this case, there was the particles that I showed in the previous images with the cathode of the batteries. We select a dedicated part of those cathodes. You remember this image was a square millimeter in high resolution, nanometer resolution. We select those particles. Then finally we make a transversal cut through these particles, make a polishment of the surface, and performs a high resolution images with this, in this case with the electron microscope inside the dual beam system. Once we did that, the next step is to correlate this contrast image that we get from this in this case, this is a secondary electron image from the electron microscope. We would like to see, we identify the different isotopes from the lithium battery inside this cross section. And this is what we did. We performed from every single point of the ECM a mass spectrum from the surface. And what we see here on the left, this is a mass spectrum of positive ions for one single point in the samples. And what we create by scanning with the gallium FIB, and this is synchronized with this with the mass spectrometer, we create to every single point a mass spectrum. And on the end, you have on the full surface a library of their full mass spectrum over the full surface. We did the same. We did the same for negative ions, also with a library of the full area. And finally, we started to correlate. On the left, you see the image from the dual beam, in this case from the SA image, from the FIB, with qualitative contrast information. And now we are starting to select the different element that we are looking for. We are seeing here the distribution of oxygen, of fluor, of different kind of carbons, but also we started to see the distribution of lithium isotopes in the sample. In this case, lithium with the mass 6 and the mass 7, which is very characteristic for this type of battery investigation and degradation after many kind of cycles. Okay, with this image, I would like to conclude my talk, and thank you again for your attention.
Thank you also. And if there are some questions from people here or online.
Yeah.
Okay, so probably everybody's budgeting now. So, yes, nice talk. Okay, so if there are no questions, thanks a lot again for your talk. It was very interesting, and it gave us a lot of ideas. And we will move towards the next talk, which will be also an online talk. Marilyn Guiou, the talk will be related to niobate ferroelectric thin films, growth and characterization of perovskite and TTB phases in the potassium, sodium, niobium oxygen system, and the potential of application in high-frequency miniature tunable devices. So the talk will start now, will be for about 40 minutes. Thanks. Hello? We cannot hear you. We see you, but we cannot hear you yet. Okay, so I think you should unmute your Zoom client. Okay, so it's unmute.
In the top bottom left corner, you have a microphone. Bottom left, I think. Now you have to select the other microphone, also from the left. You can hear us, right? Okay, perfect. Okay. So left bottom corner, select the microphone. You have multiple microphones. Take it easy. In 2 minutes we will be okay. You have to select the other. Okay.
No, yes.
Perfect.
It's okay, no.
Okay.
Okay, thank you, I'm sorry.
Okay, no problem.
For this technical problem. So, first of all, I would like to thank you, and thank you so much, the organizer, to invite me to give this talk today. And after this very impressive talk on scanning electron microscopy, I will completely change the topic. Because I will speak about niobates, ferroelectric thin films. And the work I will show you has been obtained in the frame of collaboration between different labs, essentially the Institute of Chemistry in University of Rennes and Institute of Electronic, and also in collaboration for some characterization with INL in Lyon and Grément in Tours. So the outline of my talk will be first an introduction on niobates, and especially on KNN, that will be the subject of my talk. And after that, I will present to you two results about two phases, the perovskite and the TTB, that is the tetragonal tungsten bronze phase, in the KNN system. And we will see the deposition, characterization from structural and chemical point of view, and also some illustration of the behavior in high frequency, so dielectric characterization, and I will illustrate also reconfigurable devices. So, as you know, niobates constitute a very large variety of ferroelectrics with very different type of structures, Arrhenius phase, perovskites, but also TTB and so on. All these structures are highly flexible and give many possibilities of tuning the composition. For instance, in the perovskite, we can substitute different elements in the structure and obtain many solid solutions. In the TTB structure that you can see here, there are different cavities, A, B, and C, that can be occupied by different cations, small or big ones, and it's possible to modify the composition by substitution in the main elements, but also by doping effects. So we can see some examples of this substitution: niobium by tantalum, niobium by tantalum, or strontium barium. So in potassium niobates, especially, it's possible to tune the A site in the structure and the B site. So now, why to work in the KNN system? The system that is well known is the perovskite: potassium, sodium, potassium X, sodium 1 minus X, niobium, oxygen 3. That is the perovskite of the KNN system. This material is well known for high Curie temperature, but also for high piezoelectric coefficient. And today, it is considered as one of the most promising lead-free piezoelectric materials. But this material is also ferroelectric material. And in this case, it's possible to tune the dielectric permittivity that give a material solution for high-frequency reconfigurable device. Indeed, in our lab, we work in this frame with the aim of miniaturization. This is the wide aim of the evolution of the device. And in order to obtain this miniaturization, there are different routes that have to converge. And first one is to decrease the number of devices in the different microelectronic system. That means that tunability will be one solution to obtain only one tunable device instead of numerous devices. High value of permittivity in the device, in the substrate itself or sublayer, will give the possibility also to miniaturize in high frequency. Ferroelectrics give both tunability and high value of permittivity. And depending on the operating temperature, the material will be in the ferroelectric or paraelectric phase, giving the possibility to modify the permittivity, epsilon, with the application of an electric field. And in this case, the evolution of the permittivity will give the possibility to tune the device, for instance, by changing the working frequency of the device. So, in this context, the perovskite in KNN system present, beside the piezoelectric coefficients that are promising, a quite high permittivity, dielectric permittivity in ceramics at moderate frequency, and that is still quite high at 10 gigahertz in ceramics. In thin films, there are only a few reports on thin films of KNN in high frequency. We can see, for instance, this paper dated from 6 years ago, giving epsilon R about 300 at 10 gigahertz and tangent delta of about 1%. Concerning the possibility to tune the frequency of a device, for instance, that means the tunability T, has been reported to be about 22% under 200 kilovolt per centimeter as E bias. The tangent delta is typically 20 in this application at 20 gigahertz. So all these data are related to the KNN perovskite. In this system, in this perovskite, you can see here the phase diagram. From 2% in potassium, the material is ferroelectric. Ferroelectric with the first transition at the Curie temperature that is stable, quite stable with the composition. But below this Curie temperature, another transition, so-called the pseudomorphic transition, will appear and will be different with different structural phases depending on the composition. So, how to control the thin film's properties and the KNN properties. The composition is the first solution. I will show you some examples from the literature. With the composition, we will change the structural features concerning the transition and around especially the pseudomorphic. For instance, for the 50-50 composition, 50-50 ratio between potassium and sodium, we can see that this pseudomorphic transition will be from tetragonal to orthorhombic by cooling the temperature. Changing the composition in the solid solution will tune and change these phases. Concerning the composition in the solid solution by adding doping, Saito has reporting some years ago that it's possible to obtain different and high piezoelectric coefficients, as you can see here, in comparison with different other piezoelectric systems. So it's possible to change essentially the transition, and here we can see the morphotropic phase boundaries that can be controlled between tetragonal and orthorhombic phases by tuning the composition. More recently, by nanoscale control of the composition in sodium niobate, Liu et al. Have shown that it's possible to obtain very high piezoelectric coefficients with a high Curie temperature. The nano-engineering of the composition consists to obtain heterogeneity in composition in nanoscales. For this purpose, sodium deficient, slight deficiency in sodium has been introduced in sodium niobate films. That means that the film consists of a matrix of the perovskite with inside some nanopillars that have been grown with in the sodium deficient regions. By the sodium deficiency, some modification in the structure locally at the nanoscales was implied, and by introduction of these nanopillars inside the matrix, some multi-phase boundaries with domain walls motion under electric film have been involved. It's more or less the same approach as with MPBs, but it's different and obtained only with epitaxial thin films deposited in this case by sputtering on strontium titanate. Another possibility is to tune the properties of the material by the substrate and especially by stress and orientation. You can see the example of the work performed in IKZ in Berlin in the group of Jutta Schwarzkopf by changing and monitoring the strains. In this lab, they developed single crystal substrate with appropriate lattice parameters depending on the composition of the KNN system in order to control the strain. And by strain engineering, as we can see here, it's possible to strongly change the phase transition temperature. This phase transition temperature corresponds to the pseudomorphic transition. That means that both phases, before and after the transition, are ferroelectric. This is the effect of the in-plane compressive strain, and the impact is huge. As you can see here, it's possible to tune the temperature of transition between minus 15 degrees C and 400 degrees C. So it's possible to enhance the properties because it's possible to close then the transition temperature to the operating temperature and enhance the physical effect by this way. So after this introduction on the KNN system and how to control the properties, I will first speak about the potassium-sodium niobate perovskite. After that, on the TTB. All the films have been deposited by pulse laser deposition with homemade target, sintered either by natural sintering or by SPS, spark plasma sintering. The films have been deposited in very standard conditions with an excimer laser at a temperature of the substrate between 550 degrees and 700 degrees and a typical oxygen pressure of 0.3 millibar. Two types of substrate have been mainly chosen: air-cut sapphire and magnesium oxide. We have selected with two substrates because of their suitability for application in high frequency, because of essentially a very low tangent delta and quite moderate permittivity. Magnesium oxide presents a closed lattice with K in N and a quite low mismatch of a few percent that gives a possibility to expect an epitaxy. In contrast with sapphire, a texture will be generally expected with a quite higher mosaicity. Thin films have been characterized by scanning electron microscopy, standard, only one electron beam, X-ray diffraction, theta to theta of 4 cycles diffractometer, and also transmission electron microscopy with EDX. For dielectric characterization and device measurements, metallization has been performed with titanium, 5 nanometers of titanium, then 2 microns of silver, standard photolithography, and wet etching process. The general device, more common, are 3 transmission lines that have been used to determine the permittivity and loss tangent delta, and a resonator also. The stub resonator gives the possibility to measure the resonance frequency and its variation under application of a bias to obtain the tunability. These measurements have been also performed in temperature. So, now what about the perovskite? From the thin films to reconfigurable antenna. So, we have already seen what is the phase diagram. The main composition we have studied is a 50-50 ratio between potassium and sodium, but also we have compared to 70-30. Thin films have been deposited on airplane sapphire. You can see here the theta to theta X-ray diffraction on sapphire with an orientation along the preferential orientation along the 10010 direction. You can see here the classical morphology of such films. And in this case, we have a texture, and the phi scan shows that there is some in-plane preferential orientation, but not a very beautiful epitaxy. We have similar results on the second composition. After that, dielectric permittivity and intrinsic loss have been measured at high frequency. And we can see here that for the 2 composition, the permittivity have been compared. The highest permittivity is obtained for the 50-50 composition. And then tunability has been measured. Also the losses, tangent delta is more or less the same, even higher on the 70-30 composition. And we can have a look on the tunability. That means measurement without and with an electric field. And the value of the permittivity and this tunability on both composition show that the tunability is higher on the 50-50 composition. After that, we have worked mainly on this composition, 50-50, potassium over tantalum. We obtained in comparison with a few data of the literature, a slightly higher permittivity value, higher loss but of the same order of magnitude, and a tunability of 15 to be compared to 22, but with a lower E-bias, because we are working with only 80 kilovolt per centimeter with our device that are coplanar geometry. Then, what about the possibility to change the structural quality? Thin films have been also deposited for comparison on 100 MgO substrate. We can see that similar texturation rocking curve have been measured on both substrates, sapphire and magnesium oxide, but on magnesium oxide, a beautiful epitaxy has been obtained in comparison with sapphire. And in fact, what is the impact? The impact, there is almost no impact of epitaxy concerning permittivity and loss. But if we have a look on the tunability, we can see here that the tunability is higher for 3% measured in the same conditions on magnesium oxide. You can see here the evolution of the tunability that increase above 20% for 100 kilovolt per centimeter as BIS. In comparison with sapphire, it has not been possible to increase more the voltage on the sapphire substrate. This increase of the tunability on MgO substrate has been measured with reproducibility on different samples, so it's systematic. What about the behavior in temperature? You can have a look here on the evolution of the permittivity versus the temperature for the two ferroelectric phase, orthorhombic and tetragonal. This is a pseudomorphic transition measured on the two samples, on sapphire in black and on MgO in blue. We can see that the permittivity of almost 1,000 has been obtained at 10 gigahertz in the neighborhood of the transition, a decrease of the losses, and a transition that is more continuous on magnesium oxide. If we have a look now on this permittivity, we can see the maximum around 210 and 220 degrees. But what about the tunability, that is the evolution with the voltage? We can see that the higher tunability is obtained below, just below the transition, with a maximum of tunability that has been measured at 200 degrees C, here with a variation of epsilon of 255. That means that in this system, it has been possible to tune the tunability, especially with composition and also with the substrate itself. And we obtain also we have measured the transition, the morphotropic transition, the pseudomorphic transition, sorry, at high frequency at 10 gigahertz on these thin films. These thin films have been used to elaborate in EOTR a frequency tunable slot loop antenna based on KNN interdigited varactors. You can see here the layout of this ADC varactor, so interdigited in plane varactor. The antenna fabrication, first deposition of KNN. After that, we have performed a local KNN micro-etching by laser ablation in order to confine the KNN only below the interdigitated capacitors. Indeed, we have shown in previous works that by this confinement, it's possible to strongly decrease the global loss of the device by saving the tunability. So after this micro-etching, there is still only KNN below the varactors, after standard metallization and photolithography and chemical etching, the antenna has been obtained and measured. And it has been observed a tunability of 750 megahertz. That means 4.6% for this antenna on magnesium oxide substrate. This value of tunability is equivalent on the one reported for the same type of antenna with the same size with other materials like BST. That is the state of the art today. So it's comparable. With comparison on sapphire substrate with a less epitaxial growth, less quality, we have a lower tunability of this frequency. So we have seen that with this perovskite of K9, it has been possible to obtain control growth on device. Now what about the TTB? In the phase diagram of niobate of potassium and sodium, here you can see the potassium niobium oxide phase diagram. We can see that there are many phases, especially many phases with potassium over niobium ratio below 1. And one phase looks of interest. This is the TTB, tetragonal tungsten bronze phase, that is reported for many compositions, for several compositions, to be piezoelectric. Indeed, you can see here two other systems reported in the years to present quite high piezo coefficients. So only a few data are reported on TTB in potassium niobates, and only a few reports in thin films. So what is the challenge? The challenge is to control in KNN low potassium and low potassium sodium content with typically close to 0.5 without secondary phase. And you have seen here that there are many phases that can compete. So this is really a challenge to obtain this pure phase. Precise characterization have been necessary to distinguish between the TTB and the perovskite crystalline phase. Indeed, you can have a look here on the lattice parameters, and we can see that these A and B parameters and C parameters are more or less 3 times, and 1 for C, in comparison with the perovskite. That means we have an effect of substructures that make difficult to distinguish between with X-ray diffraction only. So X-ray diffraction has been performed with transmission electron microscopy performed by Valérie Demange. And in this case, only with very complete characterization, it has been possible to distinguish between the perovskite and the TTB. So now, what about the results? So thin films have been deposited by a new target that has been prepared by SPS. The films have been analyzed by EDX in transmission electron microscopy, but also by scanning electron microscopy, and we can observe a composition near the expected one for the TTB phase. The transmission electron microscopy and X-ray diffraction patterns have shown that we have a TTB phase and a pure TTB phase. Here, in the case of films deposited on strontium titanate with 2 different orientations with an epitaxial growth. And you can see here the trademark microstructure of the TTB phase with elongated grains and in some cases nanorods. On 110 STO, as you can see here, there is only one in plane orientation and 2 types of orientation on 001 STO. So it's possible to control the epitaxial growth of such films. Now, on Sapphire, for high-frequency measurements, Sapphire is desired. Thin films have been deposited on C-Sapphire for high-frequency range. Pure phase of TTB has been obtained with this type of microstructure corresponding to the different orientation that has been observed. Some additional films have been deposited on platinum-coated silicon for low-frequency dielectric measurements. For characterization first, PFM has been performed in ENL by Brice Gauthier, and on such films deposited on 110 niobium doped strontium titanate, an heterogeneous piezoelectric signal has been observed. So the film is piezo, but it has not been possible to switch to reverse the domains because of leakage current that makes impossible to reach the coercive field. From these results, dielectric measurements have been performed. At low frequency, we can see a dielectric permittivity of 200 that is stable in this range of frequency, more or less stable, with tangent delta of 1.5%. This is the same order of magnitude of other TTB films. I remind you that this is the first time that these TTB KNN films have been characterized from an electrical point of view. So it's comparable to other TTB systems. No hysteresis loop was observed because of the leakage current, probably. At high frequency with coplanar device, the permittivity has been measured to be around 130, with more or less no dispersion between 5 and 40 gigahertz. And the losses are typically about 0.2 at 10 gigahertz. What about the possibility to obtain or to see ferroelectricity? Tunability? No tunability, unfortunately. Here we can see some measurement with application of different voltage, and there is no tunability. In temperature, what happens? Between 20 and 240 degrees, there is also no transition in this range of temperature. But we can see that the permittivity is more or less stable, like the losses. What about the structure itself? By Raman spectroscopy, performed in a quite wide range of temperature, it has been impossible to distinguish unambiguously between a centrosymmetrical structure from a non-centrosymmetrical one, because we have quite broad peak because of some disorder, local disorder in this composition and in this structure. And there is no clear evidence of any structural transition over the entire temperature range. So we have a dielectric in this TTB phase, and further characterization are required to describe the behavior, to have a better description. But for the first time, we have a better knowledge of this new TTB phase in thin films in the KNN system. For the perovskite, we have seen that this is suitable for high-frequency reconfigurable device, and we can expect to decrease the pseudomorphic transition temperature in order to enhance the performance at operating temperature. Then, this system, in conclusion, is a promising lead-free multifunctional system exhibiting ferroelectricity, piezoelectricity, so suitable for reconfigurable high-frequency device or MEMS and so on type of devices. But leakage currents have to be decreased. So I will finish by acknowledgement. I would like to thank all the co-workers who have participated to this work, So many people were involved in such studies, in the co-author, but also other colleagues working on the RAN university facilities. I will thank also funding, supports, and thank you all of you for your attention. So thank you so much.
Thank you. So before the break, we have time for a few questions.
Okay, thank you, Marine, for your nice talk and nice work. I have a question because you speak about multifunctional materials and application, and I saw just Vincent in front of me. And with a TTB phase, do you think we can get multiferroic materials by maybe changing doping or adding? I don't know. It's opening question.
Yes. Thank you, Bertrand, for this question. Indeed, in TTB phases, in other systems, there are some multiferroic properties that are, in some cases, measured and often also in different systems expected, with, for instance, the introduction of magnetic elements like iron, that is the most famous, or perhaps in some cases with manganese. I'm not sure. It depends, of course, on the valency. So I believe we have two possibilities with this TTB: to dope with magnetic element, and also to develop a composite approach with ferromagnetic and ferroelectric or pseudo-ferroelectric material. And then probably we can expect that in comparison with other chemical systems.
Thank you. Other questions?
Yes, I'm curious about the example of the varactor that you showed. So I was wondering, for applications, you showed the frequency tunability of 4.6%.
Yes.
You can hear me, right? Okay. So I was curious, what are the targets in this context for applications of tunable antenna, etc.? So 4.6, 750 megahertz is good enough, or where do we need to go to?
Thank you for this question. I'm not myself specialist of antenna, so I will give you only the elements that I know. So about this antenna, first, this tunability is low because essentially the small size of the antenna. You can see here the size of our sample. This antenna has an entire size below 10 millimeter. The substrate itself is 1 centimeter per 1 centimeter. That means that the antenna here has been globally prepared on a few millimeter square. So the gain and the tunability are low. But we have now to work on, for instance, antenna arrays in order to increase the gain. And for the tunability itself, the value, the percentage is quite low, but if we compare with not the tunability measured like here, but the tunability performance, that means with regard to the electric field, this value is quite high. So to answer more precisely to your question, I think that 4.6% can be quite enough, depending on the frequency range. Here, the frequency, the operating frequency is near 15 gigahertz. That means that here we have more than 0.5 gigahertz. That is quite high, depending then on the radiating diagram of the antenna. And this radiating diagram has not been optimized up to now, because here this first antenna was to demonstrate the concept of this tunability. So I believe that this is not completely enough. It has to be increased by the design of the antenna, by the application of higher electric field also. But this is at the same level, at the state of the art, in comparison with other material, ferroelectric material in the literature. I hope I have more or less answered to your question.
Thank you. We have one more question.
Thanks, Marilyn, for the presentation. My question is also related to some extent on the one that Jorge just put before. So one important parameter for the antenna is the tunability. That's right? And you convince us that the 5% is already good enough, let's say. But losses are very important. And in fact, I noticed that you have a tunability of 5%, but losses increases by 20 decibels. So the absorption peak, it's much narrower and broader. So to what extent this device is really applicable? Because tunability is a parameter, but absorption, it's crucial. And it seems to me that absorption in all substituted materials that you have shown to us is always increases. Tunability increases, but losses also increases. Am I correct, or is it really a problem that, or is not a problem?
Yes. Thank you for the question. Indeed, of course, losses are a problem. We have quite strongly decreased the global losses, not the tangent delta, but the global losses with the confinement of the key in N. But now, different routes have to be developed in order to decrease the losses. Personally, I'm not a specialist of antenna enough to completely answer to your question. That means, to my mind, of course, I believe that these losses are too high. That's why, from material point of view, I believe that it's interesting and promising route to try to change the transition temperature, the pseudomorphic transition temperature. If we have a look again on this graph, we can see what happened around 200 degrees. We can see that at this orthorhombic tetragonal transition, the permittivity is higher, but the tunability itself is much higher. And in the same time, we can see that just after the transition, losses are decreasing. Then I believe that this is a promising route to investigate the possibility to change either by the strains or by the composition itself to shift this transition near towards, at least, room temperature in order to save some losses.
Thank you. I would like to thank again all the speakers from this morning session and to thank all the auditors. We will have now a coffee break for 20 minutes and then we will be back with the second session of the day. Thank you.
Thank you.
Thank you.